Welcome to the full stack drill on arrays and strings. This session is designed to take you from a basic understanding of code syntax to a deep mastery of algorithmic patterns and hardware reality. As we initialize our mastery script today, we are focusing on three core modules. First, we load the memory module to understand how data sits on a physical hardware. Second, we compile syntax patterns to see how high-level languages interact with that data. Finally, we enter the standby phase for debugging algorithms, where we refine our problem-solving skills. This is not just about passing a code interview, though it will certainly help you with that. This is about engineering systems that are performant and reliable. When we say full stack drill, we mean looking at the entire journey of a piece of data from its birth in memory to its manipulation in a complex algorithm. Status is currently ready for injection, so let us prepare our mind to see beyond the screen and into the actual architecture of computing. By the end of this deep dive, you will no longer see just lines of code. You'll see memory, offsets, cache lines, optimized pointers working in all in harmony to create fast, efficient software solutions. To truly master arrays, we must start with a metal, which refers to the contiguous memory layout of your computer. Imagine memory as a long strip of numbered cubbies. When you declare an array, the computer reserves a single unbroken block of these cubbies. This contiguous nature is what gives arrays their superpower, which is constant time or O of 1 direct access. Look at the memory strip on the screen. We have values like 15, 7, 42, and 9. Notice the hexadecimal addresses at the top like 0x100 and 0x104. These addresses increase by exactly 4 bytes for each integer. This leads us to the core math of the code overlay. To find any element, the CPU does not need to scan from the beginning. It uses a simple formula where the target location equals the base address plus the product of the target index and the element size. If we want the index 3, we take 0 times 100 add 3 plus 4 and immediately jump to 0x112. This direct access is the reason why arrays are the bedrock of almost all complex data structures. When you understand this offset math, you realize why array indices start at 0 because the first element is located exactly 0 units away from the base address. While static arrays have fixed size, most modern languages provide dynamic arrays like Python list or Java array list. These offer flexibility but come with a hidden cost of growth. Look at state A, where our array is full with 6 elements. If we want to append a 7, we hit a memory wall because the next cubby in memory might already be occupied by some another piece of data altogether. To solve this, the system triggers a resize. It cannot simply grow in place. Instead, it must find a new, larger block of memory elsewhere. This process in state B shows the system allocating a new capacity, which is typically about 1.5 or 2 times the original size. It then must copy every single existing element from the old array into the new one. This copy operation is linear time or O of n, which can be expensive. However, because this happens only occasionally, we say the complexity is amortized O of 1. As an engineer, you must be aware that while appends are usually fast, they can periodically cause a significant latency spike during a resize. Understanding this growth factor and the underlying allocation strategy helps you design systems that handle large data sets without falling into the trap of frequent and costly memory allocations. High performance softwares depend on hardware prefetch and cache locality. CPUs are much faster than the RAM they talk to, so they try to anticipate what data you will need next. This is where contiguous memory becomes a massive advantage. When a CPU core requests a single byte from an array, it does not grab just that one byte. It fetches an entire cache line, which is usually 64 bytes of data from the memory bus. This means that when you access index I, the CPU has likely already prefetched neighbors I plus 1 and I plus 2 into the high-speed cache. We call this spatial locality. In the diagram, you'll see how the CPU can fetch a block of 4 integers in a single cycle because they sit side by side. Contrast this with a linked list where nodes are scattered at random memory addresses. For a linked list, the CPU has no way to predict where the next node is, resulting in frequent and slow cache misses. This physical reality is why an array will almost always outperform a linked list for a simple iteration task. When you write code, you're not just writing logic, you're managing how the hardware retrieves information. Contiguous data is the key to unlocking the true speed of modern processors. Let us bridge the gap between hardware and high-level syntax by looking at slicing and the memory implications. Languages like Python make it incredibly easy to take a subset of data using notation like data bracket 1 to 5 with a step of 2. While this is clean and readable, you must be aware that a new object is created in the process. In many implementations, slicing creates a shallow copy of the specified range. What this means is that if you slice an array of size n to get a subset of size k, the space complexity of that operation is O of k. Look at the diagram, where we select indices 1 and 3 within the stop boundary. The resulting subset array is a complete separate entity in a memory. If you're working in a tight loop and constantly creating slices of large arrays, you might unknowingly be bloating your memory usage and triggering the garbage collector. This is a classic example of where seeing the syntax is just not enough. You must see the underlying memory allocation. To optimize your code, you might consider using indices or pointers to reference parts of the original array instead of creating a physical copy through slicing. This awareness of object creation is what separates a developer from a truly software engineer. Understanding mutability is essential when comparing arrays and strings. In most languages like Python or Java, a list or array is mutable, meaning you can perform an O of 1 direct write to change any element. In the list example, we change index 0 from 1 to 5 instantly. However, strings are often immutable. When you try to append a character to a string like s plus equals x, the computer does not change the existing string. Instead, it creates a full copy of the entire string with a new character added at the end. This is an O of 1 operation. If you do this in a loop, you move from linear time to quadratic time complexity, which can paralyze an application as the string grows. This is why the best practice for building large string is to collect characters or substring in a mutable list and then use a join operation at the very end. This ensures you only pay the copy cost once. By recognize the strings are effectively specialized constant arrays that require full copies for any modification, you can avoid one of the most common performance traps in software development. Always remember that mutability dictates the cost of change in your systems. Let's look at the next slide. Now that we understand the physical and logical structure of arrays, let us look at the algorithmic patterns starting with two-pointer iteration, also known as the pincer movement. This pattern is particularly powerful when dealing with sorted arrays. Imagine we need to find two numbers that add up to a target sum of 7. Instead of using a nested loop, which would be O of n squared, we place one pointer at the extreme left and another at the extreme right. In our example, negative 5 plus 12 equals 7, which is an immediate match. If the sum had been too high, we would move the right pointer towards inward to decrease the total. If the sum had been too low, we would move the left pointer outward to increase it. This logic flow allows us to search the entire space in OFN time because each steps move one of the pointer closer to the other. This pincer movement reduces the search space efficiently and is a staple for solving problems related to the sum pairs and even reversing data in place. Mastering two-point iteration is the first step in moving from brute force solutions to optimized algorithmic thinking that leverages the sorted nature of data. The second pattern is the sliding window, which we often call as the caterpillar method. This is the go-to strategy for problems involving subarrays or contiguous sequences. Instead of recalculating the sum or the specific property of every possible window from scratch, we maintain a running state. Look at the array where a window of size 3 currently covers the values 2, 1, 7, and 7 for a sum of 10. As the window slides to the right, we do not need to add all three numbers again. We simply perform a constant time update logic. We subtract the value that is exiting the window on the left and add the value that is entering on the right. In the variables panel, you can see how we take the previous sum, subtract 4, and add 7 to get the new sum. This update happens in O of 1 time. This caterpillar method is incredibly efficient for finding maximum sums, smallest subarrays with a certain property, or long substring with the unique characters. By avoiding redundant work and only focusing on the edges of the window, you can turn a slow nested loop into a high-speed linear pass through the data. It's all about maintaining a dynamic state as you move through the array. The third pattern involves using read and write pointers for in-place modification. This is essential when you want to keep your space complexity at O of 1 by not using the extra arrays. A common example is removing all zeros from an array while maintaining the order of non-zero elements. We use a fast read pointer to scan ahead looking for a non-zero values. Meanwhile, a slow write pointer stays behind to mark where the next non-zero value should be placed. Look at the annotated logic in the diagram. When the read pointer finds the value 3 at index 4, it copies it directly to index 2, where the writer pointer is waiting. The writer pointer then increments. This allows us to overwrite unnecessary data as we go. By the time read pointer reaches the end, we have shifted all valid data to the front of the array in a single pass. This pattern is the key to memory efficiency in many low-level system tasks and data cleaning algorithms. It demonstrates the power of using multiple pointers to manage different roles within the same memory space, ensuring that your solution is as lean as possible. To summarize our findings, let us look at the time complexity in this reference table. This is a critical cheat sheet for any developer. For access and updates, arrays are unbeatable at O of 1 regardless of the case. When it comes to searching an unsorted array, it's O of n because you might have to look at every element. However, if the array is assorted, we can use binary search to reach logarithmic time of O of log n. Inserting or deleting at the end of dynamic array is generally O of 1, but we must remember the worst case O of n when a resize is triggered. The most important lesson here is the cost of mid-insertion or deletion. Because arrays of contiguous inserting is the middle requires shifting all subsequent elements to the right to make room. This is a linear time operation. This physical shifting is the trade-off we pay for having such fast, direct access. When choosing a data structure, you must weigh up how often you will be accessing data versus how often you'll be modifying the middle of the set. This table provides the mathematical foundation for making these engineering decisions and is essential for passing technical assessment and building scalable software. A master engineer is defined by their ability to handle edge cases. This is what we call as the edge case linter for your brain. When working with arrays and string, you must always have a defense against four common scenarios. First is the empty set defense. Always check if the length of array is 0 before starting your logic to avoid null pointer exceptions or empty loop errors. Second, consider the second element, single element case, as some algorithms behave differently when there is only one item to process. Third, watch out for the fence post or boundary error. This happens at the end of loops where you might stop one element too early or try to go one element too far. Notice the range in the code snippet that stops one early. Finally, always implement some bound check to ensure your index is never negative and never exceeds the length of the array minus 1. These simple checks are the difference between a brittle script that crashes in production and a robust system that handles unexpected inputs gracefully. Interviewers and senior architects look for this defensive mindset because it shows that you understand the limitations of the memory and logical boundaries of your code. We have reached the end of the full stack drill. At this point, your system status should be optimized and your understanding of memory layout should be internalized. The patterns we discussed today are now loaded into your Mentor toolkit and you are ready for deployment in real-world engineering tasks. The final takeaway is simple. Do not just see syntax. When you look at an array or a string, you should see the contiguous memory cubbies. You should see the pointers moving in pincer or caterpillar movements. You should see the offset math happening behind the scenes to find the value at a specific address. Mastery is truly the difference between just writing code that works and engineering systems that are fast, efficient, and scalable. As you move forward, always ask yourself, what is happening at the memory level and how does this algorithmic pattern leverage the hardware? Thank you for participating in this session from CSAI. Keep thinking, tinkering, and learning to bridge the gap between high-level logic and low-level reality. Your journey to technical excellence continues with every line of code you write with an engineering mindset. Status is now complete and you are officially ready for the next challenge.